Given our previous analysis of plotting bomb yields and bomb weights one against the other, we're going to now look at the detailed representation from Wikipedia. This is Creative Commons licensed. So you can see the graph. It's basically what we had before. It's broken up into a bunch of sections depending on the bombs. In the lower left, you see tactical weapons. In the middle, you can see Little Boy and Fat Man. And up top, the early H-bombs with their greater yield. So let's look at this. For example, right here, there's the weight. That's a weight of a bomb. That's 10 to the power 4, which is 10,000 kilograms. And over here, you can see the yield in kilotons. So this would be 10 to the power 3, which is 1,000 kilotons, which is 1 megaton. You will look at the graph, and there will be a little difference between what we did earlier and what you see here. There are 2 points of difference. First of all, instead of the exponents, for example, the exponent would be 3 here. It's not 3 that's written, it's 10 to the power 3 that's written. Also, you see negative exponents. And the same is true in the horizontal axis. So now we are going to deconstruct this graph to explain what the axes mean. And then we'll return to the interpretation of bomb efficiency, maximum yield per weight, and further analyses. We are deconstructing now the Wikipedia graph. And the main difference is we have exponents along the vertical axis and the horizontal axis. Let's first of all look at where we place Hiroshima now on this graph. Well, Hiroshima is 15 kilotons. We can write 15 as 10 to the power of 1.17. That's going to put us just above 1 as before. But now we're also using the bomb weight exponent in kilograms along the horizontal axis. And so we got 4.4 tons, which is 4,400 kilograms, which of course is 10 to the 3.64 kilograms. So that's where we have to go. So there's the exponent for the horizontal axis, 3.64. Slightly greater than halfway, say roughly there. There's this exponent for the yield 1.17. So that's up here. So now we go along roughly just over 1 and go there. So this is the point that we want, approximately graphed as 3.64, comma 1.17. And that is how we can place the bomb in this new axis, the new graph, with the yield exponent vertically and the bomb weight exponent horizontally. There is, however, one final point to make, and that is if you look at the graph on Wikipedia, you don't see 1. You actually see 10 to the 1 there. And you don't see 0, you see 10 to the 0. So 10 is 10 times bigger than 1. And then if we go to 2, of course, that would be 10 to the 2, which is 100. So every one of these big ticks is a factor of 10 bigger. But the exponents vary in the same manner. This goes from 0 to 1. If you take this distance and you add it to itself, you go from here to here. So you're adding 1 plus 1 again to go from 0 to 2. Well, we went from 1 to 100. That's because we're multiplying by 10 every time we change the exponent index by 1. The same is true on the horizontal axis. How about minus 1? Well, we saw before that minus 1 is a way to represent 1/10. So smaller numbers as well, not only positive numbers, but also negative numbers. Now we can go back and look at the Wikipedia graph in its full interpretation. Before that, there's a few questions to do on edX regarding where do we place the other bombs, the Grand Slam and Tsar Bomba, in this new format. Then we will return to the wiki graph.